So following our discussion about units and using scientific notation, we'll continue that theme with chemistry and measurements by looking now at the difference between measured numbers and significant figures. Significant figures tends to be a topic that most chemistry students, especially students in a course like this that's not aimed at majors, people who are not going to become chemists, tend to get frustrated with significant figures because it does take a little getting used to, and unfortunately by the time you get used to it here in 141, we barely touch it in 142. So please bear with me, do your best to take significant figures to heart, otherwise you're likely to see, especially on those labs, some sort of sig fig deduction. We don't just want to live with it, we want to understand sig figs and get them right all the time. So when we measure numbers, which is an important thing that scientists do, we need to make sure that we represent those measured numbers accurately. So we might be measuring the numbers on something like a scale, or more correctly an analytical balance, and typically the ones that we would use, it would have digital displays. So that's great, that takes care of all the uncertainty. We take every digit, but sometimes we'll have weighing by difference, where we have to take an object that doesn't sit nicely on the balance, say something spherical, and put it into another container. And so we weigh that empty container first, then we weigh the sphere in the container, and we subtract out the mass of the original container. That requires us to know our sig fig rules. A graduated cylinder, we talked a little bit ago in one of the other lectures on this chapter about the idea of estimating to the uncertain digit. So graduated cylinders are typically analog devices, no digital displays, so we do need to know about rounding and estimating. A clock or a stopwatch, that tends to be digital again. And then if we look at a ruler, that tends to be analog. We'd have to, just like the grad cylinder, have to make those final estimates as to the last decimal place. So to follow up on that last idea of estimating to the last decimal place, we look here on this metric ruler. Each of these small divisions is 0.1 centimeters, so we could write the value with certainty to the 0.1 centimeter, the 10th place, but we could look and see that we're just about in between, say, 4.5 and 4.6, maybe a little closer to the 4.6, so maybe we could estimate that it's a 4.55 or even 4.56 or 4.57. We might be off just a touch in that last hundredths place, but again, it's clearly not just over 4.5, it's not exactly on 4.5, so as scientists we do have an obligation to try to estimate that one uncertain digit. We know it's 4.5 something, it's not quite 4.6, but to our best guess, I might say 4.57, and you might say 4.56, and we'd be off a little bit from each other, but it's a much better value than just saying 4.5 centimeters. Okay, so once we have a measured number, whether that measured number comes from a digital display where every digit shown is typically taken to be significant, unless you have a mass less than 0, for instance. Then we might have some leading zeros there. But otherwise, we tend to expect every digit in a digital display to be significant, or in an analog display, again, right to that estimated final digit, we would be able to see how many significant figures we have. The rules that we would need to determine if a figure is significant would be, first of all, any number that's a non-zero number would be significant. So if we have 234 grams, for instance, we have 3 significant figures. Each of those is a non-zero digit, so they'll always be significant. If we have a 0 between non-zero numbers, then those zeros are also always significant. So in the example we see here, 50,071 grams, that's 5 significant figures because those zeros are in between non-zero digits. If we have a 0 at the end of a decimal number, so we have a non-zero digit and then we have some zeros here, 50.00 meters, for instance, that's 4 significant figures. If we had just written 50 meters without a decimal point, then it's probably just 1 significant figure. There's some doubt. If we show the decimal point, then we would have to include that 0 as well. Finally, if we express our value in scientific notation, then everything before the 10 times 10 to the whatever exponent would be significant. So if we use scientific notation correctly, right, we'll never have a 0 in the ones place. We'll always have a value between 1 and 10, and therefore, however many digits we show will all be significant. Probably the easiest way to determine the number of significant figures you have in a value, especially a very large or very small value, would be to convert it to scientific notation and then figure out that coefficient for the times 10 to the positive or negative exponent, and that would give you the number of significant figures. So here 2.0 times 10 to the positive 3 meters would have 2 significant figures. Because non-zero figures are always significant, it's those zeros that tend to cause us trouble. So if we have 1 or more zeros in a very large number, one way to show that they're significant is either through the use of decimal points or through the use of scientific notation. So we see here for 5,000 kilograms, if we want you to know that that's exactly 5,000 kilograms to the nearest kilogram, we would either write 5,000 and show the decimal point to let you know that they're all significant, or if we express it in scientific notation, 5.000 times 10 to the third kilograms. Either of these instances, we clearly see that there are 4 significant figures. Those zeros are significant. If the zeros are not significant, like we see in the lower examples, we would have only the non-zero numbers in the coefficient for scientific notation. So if we wrote 5,000 kilograms without the decimal point, or if we wrote 5 times 10 to the third kilograms, either of those examples, we would only be looking at the 5 as the significant figure and have just 1 significant figure rather than 4 significant figures, like when we showed the decimal point or wrote 5.000 times 10 to the third kilograms. Sometimes when we're doing significant figures, we have values that seem to have very few significant figures but are actually exact numbers. And exact numbers never influence the number of significant figures in a calculation. So exact numbers would be included in that term would be those numbers obtained by counting items. So if you have exactly 12 items, then that 12 isn't just 2 sig figs, it's considered infinitely significant. Likewise, those numbers in the definition comparing 2 units in the same measuring system are infinitely significant. So 1 kilogram is exactly 1,000 grams. It's not just 1 sig fig or 4 sig figs for that 1,000. It's an infinite number of sig figs. Likewise, if we had a definition of a unit, as we see in the table down below, if we had 1 foot equals 12 inches, that would be exact values. If we had counted numbers, the examples they show 8 donuts or 1 dozen would be exactly 12. We're not talking about 13 donuts or 11 donuts. If we're at the grocery store getting a dozen, we're getting exactly 12. So these exact numbers are not measured, and they don't affect the number of sig figs in a calculated answer. So they themselves have an infinite number of sig figs, and therefore it's the significant figures in the non-exact numbers, the measured numbers, that would influence the final number of significant figures in a calculated answer. Okay, so we've covered a lot of ground here with measured numbers and counted numbers and significant figures, exact numbers. Let's see how well we can apply these ideas. So here's a brief learning check. Looking at these 3 examples, let's identify the following as either exact or measured numbers. So the first value, 824.75 centimeters. Number 2, 23 students in the class. And number 3, 1 meter equals 1,000 centimeters. So for each of them, identify them as exact or measured. And for the measured number, you could even go ahead and figure out the number of significant figures. So either pause the video here, or if you're ready to move on, let's see how you did. Okay, so hopefully you were able to identify that number 1 there, the 824.75 centimeters, is a measured number that was determined probably by estimating to that hundredths place on a measuring device like a ruler. Number 2, 23 students in the class. That's an exact number, right? Hopefully, as instructors, we can count the number of students we have and not be off by any number. We get it exactly right all the time. And then finally, the third value, which is a definition of units. 1 meter is equal to exactly 1,000 centimeters. That's not 1 sig fig for the 1 meter, or 1 sig fig, or 4 sig figs even for the 1,000 centimeters. It's an infinite number of significance because we're defining a unit in terms of another unit. So, and if we go back to the very first one, that was our only measured number, so our only value that had a countable number of significant figures. Because they're all non-zero, it should be easy to see that there are indeed 5 significant figures there. So hopefully this went well for you. Otherwise, let's try again with another learning check. Alright, so looking at our last learning check for this subtopic, we have 4 values here, and your challenge now is to determine how many significant figures are in each of those numbers. So for number 1, we have 8,250 centimeters. For number 2, we have 0.012 grams. Number 3 is 8.20 liters. And number 4 is 3.040 times 10 to the minus 2 meters. So for each of those values, go ahead and determine the number of significant figures. And if you still need another moment, pause the video here. Otherwise, let's move on and see how you did. Okay, so for number 1, 8,250 centimeters, because we don't show the decimal point, we assume that 0 is just a placeholder, and therefore only the 8,000, the 200, and the 5 from the 50 are significant. So just 3 significant figures there. The final 0 is not considered significant. It's a placeholder. We could rewrite that as 8.25 times 10 to the 4th centimeters using scientific notation. For number 2, we have just the 2 significant figures, those 2 non-zero digits at the end. The first 0 and the second 0 are just placeholders to let us know that we're going into the hundredths place and thousandths place before we have anything significant. If we were to rewrite that in scientific notation, we would have 1.2 times 10 to the minus 2 grams. So scientific notation is a nice way to figure out exactly how many sig figs you have. For the third value, now we have 8.20 liters. Each of those values is significant. That final 0 is important. It's not just a placeholder. The fact that we bothered to include a 0 after a decimal point and after a non-zero digit means it is always considered significant. So we have 3 significant figures there. And finally, number 4, already in scientific notation, 3.040 times 10 to the minus 2 meters. As we said, anything that's in that coefficient before the times 10 to the minus 2 is a significant figure, and therefore we have 4 significant figures. We have that buried 0 in between the 2 non-zero digits, and then we have that 0 at the end that indicates place value that is significant. So hopefully this discussion of significant figures has gone well. If not, hopefully it spurs you to try more and look at some additional problems from the text. Get in touch with me if you continue to struggle, but please don't just throw in the towel. This topic comes up again and again throughout the course, and especially in the laboratory, so please make it a priority to learn significant figures in chemistry.